In this video, we're going to learn about two distinct functional groups that actually share a common structure, a structure that we call a carbonyl. So a carbonyl is a carbon that contains an oxygen that is bonded to it, but unlike the oxygen in a hydroxyl group, we can see that the oxygen of the carbonyl is double bonded instead of being single bonded. And we can actually make two different functional groups out of this one relatively simple bonding structure by taking a look at whether the double bonded oxygen is on a terminal carbon, meaning a carbon on the end of a chain, or an interior carbon, meaning a carbon that is surrounded by other carbons. And we're actually going to take a look at the latter first in a functional group that we call ketones. So all of these are examples of ketones because if we look for a carbon, we can see that this carbon here is an interior carbon because the terminal carbons are here and do not contain an oxygen with the double bonded O. So the carbonyl here is placed on the inside of the molecule rather than on the outside or at the terminal locations, and we can identify ketones in a name via the suffix ONE. So ketone, ONE, the suffix is quite understandable where it comes from. So this simple ketone here, we can see that the parent chain is 3 carbons long, so it would be prop, and we can see that the carbon chain, the parent chain anyway, does not contain any carbon-to-carbon double bonds, so propane is our parent chain, and then we can see here that the ketone actually falls on carbon 2. Now, why am I writing propanone and why am I not calling this propan-2-one? Well, given the definition that the carbonyl can only be on an inside carbon and not on a terminal carbon, the fact that this is propane-2-one is actually understood because there is only one interior carbon because the other two are terminal. So technically calling this propane-2-one is not wrong, just redundant because we don't need to specify which carbon the ketone is on because there's only one interior carbon to have. On the other hand, if we take a look at this molecule here, we can see that our parent chain is a pentane. Actually, I'm going to make some space here because we can see that the ketone falls on carbon 3, and on carbon 2 we have a methyl here. So this would be called 2-methyl propane, again, because not propane. In this case, we've got 5 carbons, so this would actually be pentane, because again, parent chain is 5 carbons, and we only have carbon-to-carbon single bonds, and this time, because there are multiple interior carbons where the ketone might be located, we actually need to specify that this is pentane 3-one rather than pentane 2-one or pentane 4-one like this. So here is how we would name a ketone that actually has a side chain as well. Now, cyclic ketones are actually interesting because there is no choice but for the carbonyl to be a ketone within a ring structure because ring structures do not actually have terminal carbons because each carbon within the ring connects to 2 other carbons inside of the ring. And therefore, we can simply call this cyclohexane if we identify the correct number of carbons and the fact that the ring has no double bond, nothing other than carbon-to-carbon single bonds, we can simply call this cyclohexane 1-one, although in a ring structure the functional group is automatically defined as carbon 1, so if you were to simply call this cyclohexane this would also be correct because it would be understood that the ketone functional group falls on carbon 1. Now this begs the question, what if the ketone falls on a terminal carbon? Well, then we wouldn't have a ketone at all. Instead, we will have a functional group that we call an aldehyde. And again, the only distinction between a ketone and an aldehyde is that the double bonded oxygen on a carbon falls on a terminal or carbon, or if we use the noun form, on the terminus of the molecule. And unlike ketone, where the suffix is the ending word of ketone, here we represent aldehydes by the suffix al, taking the prefix of the word aldehyde and turning it into a suffix. So for example, if we take a look at this aldehyde here, which has 2 carbons, so the parent chain would be named eth, and because there's only a single bond here, we can call this ethane. And the good thing about aldehydes is that we don't actually need to specify a number for the location at all, because an aldehyde, by definition, will always fall on an end carbon, meaning that they always fall on carbon 1 or on the final carbon of the molecule. So simply referring to this as ethanal is sufficient. Ethan1-al is redundant, in the same way that saying ATM machine, automated teller machine, or PIN number, personal identification number is redundant. Now, what if we have 2 different aldehydes that we had here? Well, we would name the parent chain normally 1, 2, 3, 4, 5 to indicate that this is a 5-carbon alkane. We would adopt the parent chain name pentane, and because there are actually 2 aldehydes here, and because aldehydes can only fall on a terminal carbon in pentane, we know that the aldehydes can only be on carbon 1 and carbon 5, so putting the numbers in is redundant, so we can simply call this pentane dial, understanding that the aldehydes need to fall on the first and final carbons of the chain. Now, in this molecule here, we actually have a side chain, or 2 side chains rather, and we actually have a double bond, which we can quickly identify is in the E position here. So if we identify that the double bond is in the 1, 2, 3, 4th location, we can specify that our double bond is in the E position because the longest carbon chains are on the opposite sides of the double bond, and then we would need to specify where the side chains are located, which would be at carbon 1, 2, 3, 4, 5, 6, or let me count again, 1, 2, 3, 4, 5, 6, 7. So our parent chain is going to be 8 carbons long, and our side chains occur at carbon 2 and carbon 7 and are each 1 carbon long, so this would be a dimethyl. And then we need to indicate our parent chain, which is 8 carbons long, so this would be an, unlike all of the previous ones where they've been alkanes, we actually have an alkene here, so we need to specify that our double bond occurs in the 1st, 2nd, 3rd, 4th position of our molecule here, and we would call this oct-4-ene dial to indicate the presence of the 2 aldehydes at the first and final carbons in the molecule. So this is why most people describe that naming aldehydes is significantly easier than most other functional groups, because the functional group will always be on carbon 1, and even if there are 2, the last aldehyde always falls on a terminal carbon like this. Before we move on to the final functional group in this series of videos, that being the acids, you can take a look at these practice problems here where we have provided you with 1 ketone and 1 aldehyde to name, and 1 aldehyde and 1 ketone to draw. And if you can successfully name and draw the structures provided, you can move on to the final video in this series, which will discuss the final functional group, organic acids.